I've developed this habit lately of making sure when I write your exam, I do it when my wife's not around. So I smile, she says I'm being too mean. Make sure she knows that.
Are you smiling?
I don't know. Yes, it is. 3.7. You guys, help me with this. No calculus. Look at that equation. What's this graph look like? I can't hear you.
A circle.
I can't hear you.
A circle.
Ellipse.
Oh, put my pin down. I'll sit for a while.
What's it? Oh, it's a subtraction.
Yeah.
So it's
Hyperbola. Beautiful. And if that's a hyperbola, can you guys tell me the intervals at which this function is increasing and decreasing? I'll ask it again. Can you tell me the intervals at which this function is increasing and decreasing? Whoa, whoa, whoa. How can a function increase and decrease at the same time? Perfectly put. Randall's saying this is not a function. I can't even discuss increases and decreases. Or he said it correctly. He said increasing and decreasing because it's not a function. It fails a vertical line test. And I haven't told you how to differentiate something that's not a function. However, I have to confess, if I used a tad bit of math D skills first, and isolated y in that equation, wouldn't I get that y squared is equal to x squared minus 1? Which means y is equal to plus or minus the square root of x squared minus 1. And now to differentiate with respect to x, I know there's two outputs, but fine, two outputs. If I differentiate with respect to x, don't I get 1 over plus or minus 2 times the square root of that stuff? Times to do the inside? Or shall I say dy dx, you guys stop me if you need to, is just simply, I don't know, is it an x over plus or minus the square root of x squared minus 1? I just think what I'm writing on the board looks awkward. There's nothing wrong with it. It's just awkward. Because technically speaking, what I just did is this. I have an equation in x and y. And what I did was I solved for y. And what I ended up getting is an equation involving dx, or excuse me, dy dx. And x. And I simply isolated x, or excuse me, I isolated dy dx. Which means in the end, I got that dy dx was equal to some junk. But what I could have done instead is I could have differentiated initially what I will refer to as implicitly and generated an equation in x, y, and dy dx, and then merely solve for dy dx. And I will generate dy dx equals some junk in x and possibly y as well. And I maintain as an abstract algebraist, these two approaches are equivalent. I can take both paths and come with the same answer. So let me impress upon you what I mean by taking the upward approach. So my second attempt. So you guys ready? This is sophisticated. Let's treat y as a function of x and differentiate implicitly. With respect to the understood independent variable x. Oh, let's just rewrite the first equation. What was it, x squared minus, I made it up out of thin air. X squared minus y squared equals 1. Is that correct? Treating y as some function x, let's you and I dive in and differentiate both sides with respect to x. But to differentiate the difference in two functions, I get the difference in the two derivatives. But to differentiate x squared with respect to x, what the heck do I get? Now to differentiate y squared with respect to x, what do I get? Oh shoot, I can't. Y is a function of x. I think there's composition here. I've got this function of x composed with the squaring function. I just differentiate the outermost function. I think the chain rule says I gotta multiply by the derivative with respect to x of whatever the innermost function was. I called it y. Now differentiate the right-hand side with respect to x, what do I get? But doesn't that imply that dy dx is equal to, I don't know, if I subtract this from both sides, divide both sides by negative 2y, does that just give me x over y? Oh shoot, did I just make a mistake? Is that different than my previous answer? Yeah, I think it's the same thing. After all, y, check this out, y is plus or minus root x squared minus 1. This is down here. I think that's just a y. I think it's the same answer, just written differently. Do you understand that I actually applied the chain rule in differentiating the second term with respect to x? That's the key to everything here.
So when you write dy dx and you multiply it, are you really just are you putting like imaginary parentheses there? I mean, how did you get the x over y?
Well, you know what? You're right. You got a point. I skipped some steps. Can I put them in?
Yeah.
I won't change my answer. I think number one, I subtract the rest of both sides.
Okay.
And I got this. And then in red, I divided both sides by negative 2y. It's just that on the left-hand side, the negative 2y's cancel.
Okay.
And simplifying the right-hand side, my negative 2's cancel, I'm just left with this. That's what I had before.
Okay, I see what you.
So, to make your action legal there, because technically you can't take the derivative of y because it's not an x, you just simply put dy dx. So if that was 2x minus 2.
In a sense, I did differentiate y with respect to x. You said I couldn't do it.
Well, because if you didn't have that y, and or is that just a statement saying that you did it?
It's a statement that I did it.
So if it was 2 theta, you'd have theta instead of the y there. Or any other variable. So
Sure, any other
2x minus 2a would be dA over dx.
Yes, I agree.
Okay.
You guys, if this step right here seems complicated, let me just hold it, I made a mistake. What do you got?
That's fair.
What do I get?
3 sin x squared times cosine x.
Where'd you get cosine of x?
Derivative of sine because it's
I like the way you said that. You said you multiply by the derivative with respect to x of whatever the heck was initially being cubed. Do you guys agree? Well, I know, that should be the cosine of x. I'm just not finishing for a reason. And if I differentiate with respect to x, you guys watch me. This squiggly line function in x raised to the third power, don't I just simply get 3 times of squiggly line raised to the times the derivative with respect to x of, oh shoot, that looks too silly. Let me try that again. If I differentiate with respect to x of this squiggly line function in x cubed with respect to x, wouldn't I get 3 times this squiggly line function in x raised to the second power times the derivative with respect to x of this squiggly line in red? Or shall I say, this is just 3y squared times the derivative for y with respect to x? Isn't that all I've really done over here? Do you guys see my point? Y some unknown function x? Okay, so I don't know what it is. I guess I can't call this garbage with my two index fingertips the cosine of x. I guess I can't rattle off the top of my head what the derivative with respect to x of squiggly line is. And maybe I can't rattle off the top of my head as an expression in x what the derivative with respect to x is of y, but I can call it dy dx, because that's what it is. It's the derivative of y with respect to x. How are they?
How are they going to equal then? It's 3y squared.
But I think everything about my hand here is nothing more than a different derivative with respect to x of y cubed. I think they have to be equal using the chain rule.
Oh, that's not a third attempt of what we were doing.
No, I'm so sorry. Squiggly line is a completely separate issue. It's just a lot of you gave me a blank look when I went from here to here. I'm just justifying with another example.
Got it.
My apologies. Okay. My example's too
ED.
hard.
Yes. No.
What is dy dx again?
It's the derivative for y with respect to x. And if y is some function f called f of x, then I think dy dx is just y prime, or f prime of x. And I think these symbols are all the same. Y prime, f prime of x, or even dy dx, they just simply represent the derivative for y with respect to x, or the instantaneous rate of change of y with respect to x.
Well, can you explain that like visually on a graph? Like what is it? What would it be like? Can you show that like what it is on the graph? Oh, okay, so it's literally just the derivative.
It's just
Take the
derivative.
derivative of like you said like a from x squared y.
Absolutely. What's the slope of the tangent line right here?
Zero.
0. So I think on the graph of this equation, the corresponding y values. What's the slope of the tangent line here? At this value of x? 0. What's the slope of the tangent line anywhere between this value of x and this value of x? It's negative. It gets more and more negative halfway between and less and less negative. As you move from this point to further to the right on the curve, what can you say about the slope of the tangent line?
Increases exponentially.
They increase. Maybe not exponentially, but they do increase quadratically.
No. Well, what if you took it with respect to y? Because dx dy.
Holy cow. That'd be tough because if I look at the inverse function, it doesn't exist.
Okay, so
You-
if you're taking with respect to the other variable, it would just be the inverse.
It would, yes, I agree. What can you say about the slope of the tangent line of the graph of this black curve to the left of that value of x? They're positive, but more and more positive I move to the left. And so I think my y values in this green curve, or the blue curve, excuse me, not green, are going to do that. So graphically, that's what's going on with dy dx. Right?
I think you mentioned this earlier, but what was the difference again between d over dx and dy dx?
Huge. Huge. Under this mapping of f, if this is the mapping of f, this is the assignment, what do we get for the output? I agree. This function f sends a number to a number by this description, this prescription. However, that may be a function that maps numbers to numbers, back in MapD, but I think this is like a function, is what I refer to as a differential operator. But I think it maps functions to functions For example, that differential operator maps x cubed to what?
X squared.
In fact, whenever I have a function that maps, I'm sorry, I misspoke. Whenever I have an operator or a process or a rule that maps functions to functions, I sometimes refer to that as a functor, as an abstract algebraist or a category theorist. And so I think, Randall, this d over dx is acting like the f. And do you realize the f is not the same thing as f of x? F is a process, f of x is an output. D over dx is a process, but dy dx, at least in this particular case, is a specific output. So I think dy dx is just another function of x, whereas d over dx says I'm going to operate, I'm going to do something, I'm going to act on some function like x cubed and transfer it somewhere else. Hugely different. I think these two beasts right here are just as different as these two beasts are up here. Did I talk about today the bread machine and the loaf of bread? Same thing over here. That's the bread machine, that's the loaf of bread. One's a process, one's an output. I think dy dx is a result of differentiating with respect to x. Whereas d over dx is just an operator saying I act on something to differentiate. You don't like that. How about this, Randall?
I've always seen them used interchangeably.
Never show me where. Oh, I'll get so upset.
I remember that last semester.
I'll be very upset to see that. How about this? Yes or no? Is that a function in x? Now listen to my choice of words in English. If I choose to differentiate with respect to x, x cubed, do I not get this? No tricks. Can I say it differently? If y is equal to x cubed, then no tricks. Do you agree that to differentiate y with respect to x, I get 3x squared? So I think this is simply saying I compute a derivative. This is saying I'm going to differentiate. Randall, one more thing. Let me really shake you up. No tricks. Do you not agree that on the left-hand side, I can rewrite this way? I'm differentially operating on x. Sorry, I misspoke. Sorry, I really did misspeak. I meant I'm differentially operating on y.
So the y is just not written, it's assumed.
It is. As a matter of fact, watch me make a substitution. Let me call y what it really is. Actually, I forget. I got to look up. Oh, y was equal to x cubed. Isn't that exactly what I have up here? I think it's the same thing, just in a different language. Again, this is like a mathematical hammer. You're going to ding on something, and the dinging of the hammer itself is to differentiate as a process. But once you write dy dx, you've already differentiated.
Does dy of dx of 3x squared equal d of x?
See, that's what's so confusing.
No, I see your
What
point.
was the question?
No.
Okay.
I think to differentiate with respect to x, the derivative with respect to x of x cubed is to differentiate with respect to x of, let's do it. To differentiate x cubed with respect to x gives me 3x squared. Oh, but now to differentiate that with respect to x, don't I just simply get a 6x?
So it'd be a double.
A double derivative or second order derivative is what I would refer to as. And if the original function represented a position function, its derivative is velocity, and its second derivative, the second derivative of the position function is acceleration. The third derivative of the position function is the jerk function. Good. Holy cow! Did I only look at one example?
We're on our second.
I never finished writing it, did I? My apologies. Let's make it interesting. Find dy dx. You guys, I can't prove this without a, shoot. 2.5 more years of math classes. I can't prove it, but I will be able to prove it to you in a couple of years. There's no way you can solve for y in terms of x. Because it's embedded in both a transcendental function and an algebraic function. I can't isolate y in terms of x, so I have no choice. I have to use implicit differentiation. So, here I go. Treating y as a function x. Let's differentiate. Implicitly. With respect to x. Now I confess, why actually in this example truly is not a function x, but if it were, then to differentiate the very first term, what differentiation rule would I have to use? What differentiation rule? What differentiation rule? The product rule. And the product rule says if differentiate the first term, I get the first as is. Times through the second. Watch me, watch me. Times the derivative with respect to x of the second function. Plus the second function times the root of the first. Sorry, I made a mistake. I really did make a mistake. I said root of the first. What is root of the first respect to x?
2x.
Moving to the second term. I think over there, to differentiate, I'll have to use the, what kind of rule? The,
Product rule.
still the product rule. I get the first. Times the derivative of the second with respect to x. But the derivative of the second with respect to x is differentiating y squared with respect to x. Don't you guys agree there's composition here? The squaring function and this unknown function in x I called y? The outermost function is a squaring function, so I better differentiate the outermost function first. I will bring down the 2 down to the level of everything else by multiplication, reduce my exponent by 1. But the chain rule says I gotta multiply by the derivative with respect to x of whatever was initially being squared.
Why?
Oh shoot, I'm not done with the product rule. Plus the second as is times the derivative of the first with respect to x, which is just
1.
and this is equal to the derivative of the right-hand side with respect to x. What's the derivative sign of anything?
Cosine of any.
The cosine of that thing. Oh, but shoot. The product rule says, excuse me, I misspoke. The chain rule says now I gotta multiply by the derivative. What the heck I was taking the sign of? But cheaper to differentiate what the heck I was taking the sign of means I gotta apply the product rule again. Let's do it. That gives me the first times the derivative of the second with respect to x, plus the second times the derivative of the first with respect to x. Gosh, you guys, I just lost track of what I'm doing. What am I trying to find? dy dx. What power is dy dx every time you see it in this equation? First power. So that means this kind of equation is a, what's a math? No, math. A question, isn't it? It's just a linear equation in dy dx. All I have to do is bring all the terms involving dy dx to one side, all terms involving to the other side. It's a math A question. Oh shoot, I can't. I don't see what terms involve dy dx because the multiplication's in the way. Allow me. I'll remove this outer set of parentheses. And maybe with my red pen, I would clearly identify what I'm trying to isolate. Hold on, I'm running out of room. Just a second. Hold that thought. Red pen. I think what I have sitting in front of me. Oh, I can't read that far. Is that an x squared? Just make sure I'm writing down the right symbols. Is that an x or a dy dx? Is that a plus 2xy in black? And is that a plus 2xy dy dx?
Was that supposed to be y prime?
No, it was a y to the first power.
Oh, okay.
Plus a y squared. Being equal to an x cosine of xy dy dx. Is it a plus y? Cosine stuff? Well, now you guys can clearly see which terms do involve the red variable, the red unknown, the red thing I'm trying to isolate, and the terms that don't involve it. So let's you and I bring all the terms involving dy dx to the left-hand side. I'll leave this one here. I'll leave this one here. I'll bring this one to the left-hand side. On right-hand side of the equation, I'll leave this here. Oh shoot, I missed a few things. I got an idea. Take this black term and subtract it from both sides. Oh shoot, there's another one. Take this black term and subtract it from both sides. At least now I got all the terms involved in the red thing to the left-hand side, everything else to the right-hand side.
Is that an equal sign?
That is an equal sign. It's supposed to be an equal sign. It's just in a different dimensional space. You can't see it. Yeah, flat. There you go. Oh shoot, you guys, I don't like this. I want to see the red thing only once. How can I see it only once?
Factor it out.
Pull it out, factor it out. And if I factor it out, don't I have the dy dx times black stuff? Is equal to more black stuff? And now isolating dy dx my equation by dividing both sides by this black stuff, don't I really get this? Oh, I put you to sleep, I'm sorry. I'm sorry, you guys, I can't say this enough. This is really important. Do you understand my steps? I know I'm at the board tonight. I'm not going to do anything more extreme than this in terms of being so abstract and not meaningful in terms of interpretations. I promise you I'm going to put this to applications. If you want to read ahead of me, I'm talking about solving problems that we refer to often as a related rates problem. But I need to get down the tools of implicit differentiation first.
So you could derive one of the inverse trig functions by just doing the same thing with, that's how you do it with the triangle, right?
Absolutely.
All right.
I'll try to force the issue tonight before we're done. I'll try to. You guys help me with this. Can I differentiate a power function? What do I get?
N dx, n minus
Can I differentiate with respect to x the natural exponential function? What do I get?
1 dx.
Can I differentiate with respect to x this specific exponential function based on something other than e? The natural log of the base times theta dx. Can I differentiate with respect to x the natural log of x? Oh shoot, I haven't discussed it yet, have I? Oh,
1
okay.
over x.
I'll take it. How did you get that?
Hello, we are calling regarding an important business.
It is important. It is important. I'm glad you called this. I'm sorry, that couldn't have been better timing. Do you guys remember Math D? Yes, you do. You're experts at Math D. And in Math D, the log of a sum is? Nothing. Maybe the log of a product is a sum of two logs. But that's multiplication on the inside converts to addition on the outside. When it comes to addition on the inside, I don't have any properties of logs that allows me to simplify this. And so I think if you guys don't want me saying, to differentiate the natural log of x, maybe it is a case that my definition of limits doesn't really help me much. So here's what I gotta do instead. I want to let y be equal to the natural log of x. And we wish to find the derivative for y with respect to x. We want to find y prime. And so I think what I could do instead, since I don't know much about logarithmic functions in terms of calculus, let's give it up. Let's just you and I exponentiate both sides. Let's treat y as a function in x and differentiate implicitly with respect to x. But to differentiate e to any power, don't I get e to that power right back? It's just that the chain rule says I got a multiplied by the derivative with respect to x of whatever is raising e to the power of, which is y. And I need to differentiate the right-hand side with respect to x. Now, solving for dy dx, doesn't that say that dy dx is equal to 1 over e to the y? Don't take this the wrong way. There's nothing wrong with what I'm writing. It's just that if I can, and I can't always do this, but if I can, I like to kind of, I don't know, if I can replace everything on the right-hand side in terms of x. Well, look, e to the y had another name of, and so I think the derivative of the natural log of x with respect to x is just simply 1 over x. It's very cool. No, I didn't mean to say that. It's beyond cool. I mean, you guys, in your past, you've seen so few relationships between transcendental and algebraic functions. That's a really big deal. What is another relationship you saw between transcendental and algebraic functions? Building suspension bridges? Yes? No? Help me.
Building suspension bridges.
Yes.
Can you tell me how you got 1 over x from 1 over e to the y again?
Well, isn't e to the y just simply x? I made a substitute.
Oh, okay. I see.
You guys are scaring me.
It's all the homework you're giving us. Tired.
Ink's running out of his pen like crazy.
Yeah, is that 2 more o'clock?
Colorado. Oh. Squared.
The hyperbolic cosine, one yes. Hyperbolic cosine of x? And if I were to graph this thing, it kind of look like this. And if I grabbed a couple of you guys in this room, or males or females, sorry, that may be gender biased, 2 people holding a rope or a chain in between each other, there's a natural side to it, and that represents the graph of this curve with some coefficients there. We call it the catenary curve. You flip it upside down, travel across the country, you see the St. Louis Arch. Oh, sorry.
But if they're dancing like that, won't it change?
Yes, if they're dancing, there is an oscillation. They're not dancing, they're standing still. But, if I evenly distribute the weight underneath this chain, or this rope, like a roadbed of a suspension bridge, it changes the curvature in such a way that it now is mathematically modeled by an equation like this. Oh, come on, you guys didn't jump.
Oh my goodness.
Thank you. It transforms from a function to an algebraic function. Did you guys use some pre-calculus? Actually, I often teach as a Math D. No? Yeah. Okay, never mind. Another example where there's a relationship between a transcendental function and an algebraic function. Okay.
Deep breath.
Oh, you know what, you guys? That was so much fun. Let's do it again.
Okay.
If I were to differentiate with respect to x, the natural log of this.
A what? Oh, negative.
Negative x.
Don't I get 1 over whatever I was taking the natural log of?
Yeah.
Oh, wait, hold it. Chain rule says I got to multiply by the derivative with respect to x of whatever I was taking the natural log of. But that's just simply. But that's just simply. Oh shoot! That means in the end, to differentiate with respect to x, the natural log of x, whether x was positive or negative, still gives me 1 over x. That's really cool stuff.
That is insane.
No, it's beautiful.
And a beautiful kind of line.
Insanity does come into play when it comes to a 2-liner. We disagree.
Is that supposed to be a negative however x?
Where?
Very, very last one.
No, that's the derivative with respect to x of the natural log of the absolute value of x.
Oh, absolute value.
Well, I thought
Yes.
it was
everybody. You look in the left-hand board. The only thing that differentiates so far is a natural log. I don't see it. Can you force me to see it? Can you force me to see a natural log? No calculus, just math D. Math D. Can you force me to see a natural log? I said math D.
Yes.
Natural log?
Oh, you're killing me. Math D.
I told you to do it.
Change
How
your
Do you agree with this? Jeepers. You make me do everything.
Of X over log V.
Yeah.
Oh, yeah.
You know, I don't care if it's math 30. If you guys want to take a break and prove these things, I'm very happy to prove them.
It rings a bell.
What can B be? It could. What else can it be? Anything a Dharma please, as long as it's strictly positive.
E.
I'll choose E. I want a yes or no answer. Is that a constant? I'll pull it out. I want a yes or no answer. Can we differentiate the natural log of X? Oh shoot, you know what that really means? That means I get to add to my list. That means to differentiate with respect to X, the log of X respect to whatever base you darn well please, as long as it's strictly positive. I merely get 1 over the product of the natural log of that base times X itself. That's my new differentiation rule for the logarithmic function.
Ln 2 times 2dx times plus 2dx.
Zero.
1 over e.
1 over.
1.
It's just a constant.
1 over natural log of X, or 2 natural log of X.
Are we masters of differentiation? I didn't do anything wrong.
Can you just
Just one.
can you just do ln x squared minus ln y cubed?
Always apply math D skills first. I think before I differentiate, I should say that y is equal to nothing more than, go further than that.
Natural log.
2
2 natural log of X
minus.
Minus 3 natural log of
3
Y.
natural log of Y, and differentiate implicitly. And I see that dy dx is nothing more than 2 over x plus, well, I misspoke, sorry, I'm sorry, minus 3 over y times dy dx. Oh, that means dy dx plus 3 over y dy dx is equal to 2 over x. But that means 1 plus